He's a PhD student currently with Professor Nitorotaru, and today he's going to present some of his recent work on automated attack discovery in transport protocols. And this paper just recently won the Best Paper Award at DSN 2015, which is a top cybersecurity conference. So take it away, Sam.
Thank you, Brendan, for that introduction. My name is Samuel Jero. I'm a PhD student here. Today I'm talking about my work on automated attack discovery in transport protocol implementations by leveraging the protocol's state machine. I should mention that this is joint work with Hyojung Lee, who's now at Google, and my advisor, Christina Nitorotaru. The motivation for this work is that network transport protocols form a crucial component of today's internet, underlying a large majority of the applications that we use every day, from web browsing to email, instant messaging, file transfer, and many others. Additionally, the security protocols like TLS that we use for secure communication also rely on these transport protocols and the guarantees they provide. And even the network infrastructure protocols like BGP that keep the internet functioning correctly rely on these transport protocols. This then leads to a second component or characteristic of these protocols, which is that there are numerous implementations of them. Pretty much any network-connected device you can imagine, your traditional desktop devices running Windows, OS X, Linux, your mobile devices running iOS and Android, your servers, BSD, Solaris, even your hypervisors, routers, and the embedded devices you forgot you have, all will have an implementation of some transport protocol on them. However, there is a third characteristic of these protocols that we want to look at today, which is that they're incredibly buggy. This figure shows the attacks recorded in the academic literature on a single transport protocol, TCP. You'll notice that they span some 30 years of time, and that there are a couple of these attacks that have been rediscovered 10 or 15 years after the fact as still being relevant to implementations at the time. I'd also point out that these are only attacks in the academic literature. If you look at the run-of-the-mill vulnerabilities reported in the implementations, it gets much worse. These are vulnerabilities reported to the National Vulnerability Database for TCP implementations over just the last few years. So this should, of course, beg the question, why? Why, after 30-ish years, do we still have buggy TCP implementations? Why is it so hard to correctly implement these protocols? And there are a number of reasons for that. The first of these is that there are many designs and variations, particularly for TCP, and especially its congestion control algorithms. There's just a number of different algorithms that have been proposed over the years. In fact, if you look at trying to implement TCP, you'll find that there are over 20 RFCs that define components, variations, or features of the protocol. And of course, this is beside the hundreds of implementations of these protocols that I mentioned a moment ago. Additionally, transport protocols are typically trying to solve fairly complex goals. Things like reliability, which is going to require sequence numbers and acknowledgments, as well as timeouts and retransmissions. In-order delivery, congestion control, which is a whole huge research area in its own right, and a number of others that I'll mention in a few minutes. Further, these implementations are typically written in low-level languages like C and as part of the operating systems, meaning that they're highly efficient but fairly error-prone. And then, of course, because most of us like to have the fastest, most optimized networks, these network protocol implementations are typically highly optimized for performance, often at the cost of ease of understanding and maintenance, further increasing the probability of bugs. So at this point, we should be asking, well, what are the current methods for testing these protocols? How do we currently try to find bugs and vulnerabilities in these implementations? And there are a number of different methods in use today. The most common of these are developer test suites, which are tests manually written by developers to make sure their implementations are functioning correctly. Unfortunately, they tend to be fairly ad hoc and focused on benign scenarios and basic protocol functionality. Another testing method is fuzzing, which attempts to find crashes by subjecting implementations to random inputs. Unfortunately, the use of randomness makes it very difficult to cover the entire protocol, and particularly to reach deep protocol states that require multiple interactions with the protocol. Another testing method today is a tool called MAX, which is designed to automatically find manipulation attacks by using symbolic execution. Unfortunately, it requires the user to have access to the source code, to have the source code written in C, and to be able to select particular lines of code that may be vulnerable that Max can then attempt to repeatedly execute, to drive the execution toward those lines. This severely limits the number of implementations to which Max can be applied. Another testing method today is Turret, published in ICD-CS 2014, which is designed to find performance attacks on distributed systems by using a greedy message-based modification algorithm. Unfortunately, this greedy search strategy does not work well for transport protocols, and we'd really like to be able to find more than just performance attacks against these protocols. Things like resource exhaustion attacks or fairness attacks, things of that nature. So we're left asking the question, how do we automatically test unmodified implementations of transport protocols in a systematic manner? And our answer to that question is SNAKE, for State-Based Network Attack Explorer, which is able to test unmodified protocol implementations using message-based attacks and to find performance, resource exhaustion, and fairness attacks. We leverage the protocol's state machine to enable efficient and systematic testing, and we're ultimately able to find 5 new and 4 known attacks in 5 protocol implementations of 2 protocols in 4 different operating systems. So at this point, I spent a few minutes giving you some background into our motivation for this work. We're now going to look at transport protocols in a little bit more detail before diving into the design and implementation of our system, some evaluation and results, and then a brief summary. By the way, I should mention, if there are questions, feel free to interrupt me at any point in time. So transport protocols. We've talked a little bit about transport protocols already. We've said that they are heavily utilized on the internet today, that there are numerous implementations of them, and we've looked at a few of the complexities involved in their implementation. However, more formally, transport protocols are responsible for end-to-end communication in the network. That is, for moving data from an application on host A to an application on host B. They also typically provide a number of guarantees to applications. Things like reliability, which ensures that the data that is sent will eventually be received, even if it was dropped in the network and needs to be retransmitted. This requires sequence numbers, acknowledgments, as well as timeouts and retransmissions, and we'll talk about one method for doing that in a few minutes. Closely related to reliability is the idea of in-order delivery, which ensures that data that is sent will eventually be received in the same order that it was sent, even if the network reorders the data in the meantime. Another common guarantee is flow control, which is designed to prevent the sender from overrunning the receiver, and is typically implemented by specifying a window of data that the sender is able to, or that the receiver is able to receive, and preventing the sender from overrunning that window. Then there's congestion control, which is designed to prevent congestion collapse in the network, where the network becomes so overloaded it spends all of its time sending data that's going to eventually be dropped, resulting in catastrophic drop in application level performance. And I should point out that there are more than 13 RFCs that deal with congestion control for TCP alone. This is a very complex research area. We'll look in a little bit more detail in a moment or two. Closely related to congestion control is fairness, which is the idea that if you have two flows competing for bandwidth on a bottleneck link, they should share that bandwidth roughly equally. In order to provide these guarantees, these protocols need to be able to maintain state, which means they're going to need to be connection-oriented. And this means that the data transfer is broken down into three phases. First, a connection establishment phase, where the two sides synchronize their state. And then a data transfer phase, where the actual data is transferred. And finally, a connection teardown phase, where the two sides agree they're done sending data and release any state they set up. To help make this a little bit more concrete, we're going to look at TCP, or the Transmission Control Protocol, in a little bit more detail. This is the most common transport protocol in use on the internet today. You'll notice in this diagram that we have that I've highlighted each of the different stages of the protocol that I mentioned before. So we start with the connection establishment phase, with the client sending a SYN packet to the server containing connection options and its sequence number. The server responds with a SYN-ACK packet and its various options and sequence number, which the client then acknowledges. At this point, the connection is established. Both sides have exchanged sequence numbers and created any shared state necessary for the connection. The client is then can then begin to send its data. Any packet in the data transfer phase has the ACK flag set. So you'll notice that all of these packets have ACK. However, some of these packets contain data, and some of them are just pure acknowledgments without any data. So what we see here is we see the client sending 2 packets of data to the server. The server responds with a pure acknowledgement saying, yes, I got that data, you don't need to retransmit it. And then in this particular example, the server sends 2 packets of data to the client, which the client acknowledges and says, yes, I got that. At this point, the data transfer phase is done. The client can initiate connection termination by sending a FIN packet saying that it's done sending data. The server acknowledges that with the FIN-ACK packet, and the client finishes the process by acknowledging that. At this point, the connection is complete. All state can be released. We'll now look at a couple of the guarantees that TCP provides in a little bit more detail. The first of these is reliability, which we've talked about already. Provides it allows the sender, or ensures the data that's sent will eventually be received, and requires sequence numbers, acknowledgments, timeout, and retransmissions. So the way this works is that TCP conceptually labels each byte of data to be sent with a sequence number, and then each packet contains the sequence number of the first byte of data in that packet. And most packets contain an acknowledgement number indicating the next byte of data that is expected. So all data prior to that point has been received correctly and is acknowledged. Whenever a packet is sent, then TCP starts a timer, and if that data is successfully acknowledged, the timer can be stopped. If the timer ever expires, it means we didn't get an acknowledgement in time, and we can retransmit the data. There's an example here on the right that may help to illustrate this. Another guarantee that TCP provides that we'll look at is congestion control. We've said that congestion control is designed to avoid a heavily overloaded network that results in drops in application level throughput. TCP assumes that packet losses indicate congestion, which means that it should slow down as a result of that. The particular scheme that TCP uses is called additive increase, multiplicative decrease, which means that in normal operation, TCP will slowly increase its sending rate 1 packet per round trip. And on a packet loss, indicating congestion, it will exponentially decrease its sending rate by cutting it in half, resulting in a sawtooth pattern like you see on this slide. Okay, so now we've looked at transport protocols in a little bit more detail. We've looked at TCP in particular and as an example of these protocols and some of the complexities involved in their implementation. Now we want to look at security and TCP and why we care, basically. So it turns out that the majority of internet traffic relies on TCP, which means that any attacks on this protocol will affect a massive number of services and huge quantities of traffic. So web servers, email servers, instant message clients, file transfer, SSH would all be impacted by attacks against TCP. Further, the majority of network-connected devices have an implementation of TCP as the most popular transport protocol on the internet, which means that things like rarely updated embedded devices are almost certainly listening on at least some TCP port. If you can exploit said TCP implementation, you get access to said rarely updated embedded device. Similarly, high-value servers and core internet routers also have implementations of TCP, meaning that exploits can be very powerful. Further, the secure communication protocols like TLS and SSH rely on TCP, and it turns out that in some instances, breaking TCP can break these protocols. Particular example of that is the TLS truncation attack, which I've illustrated at the bottom of the slide. The idea here is that you have a secure connection to a web server with standard TLS plus TCP running on top of TCP, and then you go to try to log out of this website. Unfortunately, there's an attacker in the middle that sends a TCP reset packet, terminates the TCP connection, by implication the TLS connection that's running on top of TCP, and it appears to the client as if they're successfully logged out when in fact their credentials are still valid. If this client is, say, a shared public computer, this can have major consequences. Okay, so we're now going to take a look at one attack against TCP to help clarify what these attacks can look like. This is the TCP close-weight resource exhaustion attack. It is an actual attack against TCP that we found using Snake, and that was previously unknown in the literature. This attack allows a client to force a server to keep socket state around for 13 to 30 minutes, tying up valuable memory and socket resources. The way the attack works is that a client connects to some server, requests a large data transfer, think an HTTP file download. Then the client application exits, and the client's TCP implementation is supposed to respond to all future data from the server with reset packets as specified by the TCP specification. If, however, those reset packets are dropped, invalidated, or simply not sent at all, then to the server it will appear as though an entire window of data has been lost, and the server will back off and attempt to retransmit, which will of course never succeed. The Linux implementation of TCP will continue this process for between 13 and 30 minutes, depending on the round trip time, before finally giving up uncleanly terminating the connection and releasing resources. This 13 to 30 minutes gives an attacker plenty of time to repeat this attack hundreds or thousands of times, using up all available system resources and potentially taking down the server, or at very least denying access to legitimate clients. Okay, so we've now looked at transport protocols, we've looked at TCP in detail, we've looked at an example attack on this protocol. So now we want to step back a moment and think about the general types of attackers that might be interested in attacking transport protocols. We consider two types of attackers in this work. First, malicious clients, which are attackers that attempt to connect to some target server, either to attempt to exhaust its resources or to gain more than their fair share of network bandwidth relative to some competing connection, some form of fairness attack. The TCP close-rate resource exhaustion attack that I just mentioned falls into this category. The other category of attacks is by off-path attackers. And these are attacks where the attacker attempts to inject data into some target connection between a client and a server, either to prevent that connection entirely or to degrade its throughput and therefore its usefulness. Okay, so the question we now want to consider is how do we go about finding these type of attacks in an automated manner? The solution to that is some form of attack injection scheme. That is, we want to identify points where we can insert some form of message-based attacks into our test scenario to attempt to find attacks on these protocols. Note that the attack injection scheme that we pick will impact both the practicality and effectiveness of our testing. Practicality because systematic, exhaustive testing is going to need to test all of these attack injection points, which means there need to be relatively few of them. And effectiveness because our testing is only going to find vulnerabilities that occur as a result of injecting our message-based attacks at these attack injection points. With that in mind then, one possible attack injection scheme is packet send-based attack injection. The idea here is that for each packet, we're going to inject each of our message-based attacks at each packet send. The benefits of this approach are that it's simple and easy to implement. The downsides are that it doesn't support injecting new packets into the network. So while we can easily modify existing packets in our connection, we can't inject new ones, which means we'll be unable to find the entire category of off-path attacks that I mentioned a moment ago. Additionally, as I've currently specified it, this only considers modifying a single packet per test. So if we modify packet 2, we can't also modify packet 3, for instance. This means we'll be unable to find the TCP close-rate resource exhaustion attack that I mentioned because that attack requires modifying multiple reset packets. However, it turns out that's not a huge limitation here because even as I've specified it, packet send-based attack injection simply isn't scalable. Our 2-minute TCP tests generate about 13,000 packets, which would take us 956 days of computation to test. Fairly impractical. In addition, as I just mentioned, packet send-based attack injection misses this entire category of off-path attacks that we'd really like to be able to find. So to help with that, we can consider time-based attack injection. The idea here is that every n seconds, we're going to inject each message-based attack and observe the result, where n represents some trade-off between the scalability and the coverage of our testing, and about the smallest value for n that makes sense is the time to transmit a minimum-sized packet. The benefits of this approach are that it supports injecting new packets into the network, so we can find that category of off-path attacks that I talked about. The downsides are, again, we're only considering applying a single modification or packet modification or injection per test, which means we still can't find the TCP close-rate resource exhaustion attack. However, again, this is not a huge limitation because even as I've specified it, time-based attack injection can't achieve good scalability and high coverage. If we pick a small value for n for high coverage, like 5 microseconds in our particular test, we ended up with 12 million possible injection points, which will take us 24 million hours to test, which is fairly impractical. Since then, both packet send-based attack injection and time-based attack injection are impractical. We propose protocol state machine attack injection, which leverages the protocol state machine to provide improved scalability and coverage. On the right-hand side of this figure is TCP's state machine. You'll note that the state machine identifies key protocol areas. So the top several states are the connection establishment phase that I mentioned. The established state in green in this figure is the data transfer phase, and then the bottom several states are the connection termination phase. The key idea here is that similar packet types received in the same state often result in similar actions. So an acknowledgement packet received in the established state will always result in resetting the retransmission timer and sending new data if new data is available. However, in the SYN received state or the last act state, very different things happen on the reception of an acknowledgement packet. So what we attempt to do is to combine the protocol state and the packet type for our attack injection. Specifically, we consider the protocol state and packet type pairs and apply each of our message-based attacks to each of these pairs. The benefits of this approach are that it's scalable. It takes us about 300 hours to test an implementation of a transport protocol with this method. And we can apply our attacks to more than just a single packet at a time, enabling us to find, in fact we did find, the TCP closed-weight resource exhaustion attack. The downsides of this approach are that it assumes that the state machine is available. In practice, this turns out to not be a huge issue because for most transport protocols, the state machine is explicitly specified in the protocol's RFC specification document, usually as an ASCII art diagram that's easy to convert into the representation that we use. We also need to assume that the state machine is implemented correctly by the implementation under test. Again, in practice, this turns out to not be a huge issue because a state machine that's implemented incorrectly usually results in interoperability or basic protocol functionality bugs that a developer test suite is designed to detect. Okay. So protocol state machine attack injection forms the core of our Snake attack finding tool. Snake is divided into two components, a controller and an executor. The controller takes as input the packet formats and protocol state machine and uses protocol state machine attack injection to generate a number of strategies to test. These are then sent to the executor or executors to attempt to test and determine whether there are actual attacks involved. We run our unmodified implementations, protocol implementations, in virtual machines and connect these virtual machines to an emulated network. In front of one of these virtual machines, we place a malicious proxy that performs our attack injection. This proxy supports a number of different basic message attacks, things like dropping, duplicating, delaying, modifying packets, or injecting new packets singly or in sequence. We'll talk more about the message attacks and why we chose these message attacks in more detail in a few minutes. However, our malicious proxy also has a component that tracks the protocol state of both sides of the target connection, because we need to do this in order to be able to perform protocol state machine attack injection. We need to know what state both sides of the connection are in. And to do that, we're going to track the packets that the endpoints exchange and compare that with the protocol state machine. Okay, so during testing, we collect performance and resource usage information to be able to identify attacks. Specifically, we declare our attacks successful if we observe unfair competition between the flows in our test, which is to say that we observe throughput that's above or below the competing flows by more than a factor of 2. We also declare an attack successful if we observe that there are server resources that are not released properly at the end of our test, indicating a potential resource exhaustion attack. Okay, so the message-based attacks that we use, we developed through a careful examination of literature on existing attacks on these protocols. The first of these is to simply drop packets. This particular action will tend to expose bugs in reliability or in-order delivery of transport protocols under test. We can also duplicate packets, which will tend to expose bugs in fairness or congestion control. Our malicious proxy also has the ability to delay packets, which will cause reordering and possibly retransmission, and also interferes with the round-trip time estimation algorithms that form part of the reliability component of many transport protocols, which means that it tends to expose bugs with reliability in order delivery. Another message-based attack that we included in our malicious proxy is the ability to batch packets together. That is, to collect a bunch of packets for a couple seconds and then send all those packets out as a single large burst. This is likely to cause issues with fairness and congestion control algorithms of various transport protocols. In fact, there are a couple of published attacks on TCP that operate in a manner similar to this. We can also modify or lie about all of the packet fields in the packets our malicious proxy intercepts. We can either set minimum, maximum, or random field values, or modify the existing field values in these packets. And this will tend to expose bugs in packet validation logic across pretty much the entire protocol. It's a very powerful action that can have very diverse consequences. Our malicious proxy is also capable of injecting packets into the network. We can inject single packets using the inject action, and doing this is typically to target the handling of invalid or unexpected sequences of packets. So, for instance, for TCP, we might consider a packet with the SYN, FIN, and ACK flags all set. This would be a packet that starts a connection, terminates a connection, and acknowledges data in the connection, which is clearly an invalid combination. The final message attack that our malicious proxy supports is called hit sequence window, and it's designed to inject many packets into the connection with sequence numbers that span the entire possible sequence range in an attempt to find attacks that are similar to known reset or SYN reset attacks on TCP. Basically, these attacks are conducted by off-path attackers who spoof control packets into a target connection with the result that the connection is terminated. Okay, so now we've looked a lot at the design of Snake and at the particular message-based attacks that we implemented with our malicious proxy. Now I want to take just a moment to talk about our implementation. I've mentioned before that Snake is divided into two components, a controller and an executor. The reason for doing this is that it enables effective parallelization of our testing strategies. So we can run many executors on multiple machines to quickly test the different possible attack strategies that our controller generates. The executor itself consists of a Perl script to coordinate our virtual machines, our emulated network, and our malicious proxy. And the malicious proxy is built into NS3, which we use for our emulated network. I should also note that our implementation requires two inputs from the user. First, a description of the packet formats written in a simple language that looks a lot like C structures, and a description of the protocol state machine written in the .graph language. For our evaluation, we tested two transport protocols, TCP and DCCP. DCCP is a relatively new transport protocol designed for use in real-time video or VoIP applications. We tested 5 implementations in 4 different operating systems of these protocols, in Linux 3.0, Linux 3.13, Windows 95, and Windows 8.1. Yes?
Why Windows 95?
So Windows 95, because we figured we'd be able to find a number of bugs in Windows 95. So we figured that would be a good implementation to be able to test, to show that we can effectively find bugs. In particular, there are a number of well-known TCP attacks that Windows 95, being an older operating system, is vulnerable to, that some of the new operating systems have already fixed. So it gives us a historical test point, a historical data point. That's the way to put it. Protocol state machine attack injection found 5,500 attacks against TCP and 4,500 attacks against DCCP. Our total testing time per implementation was about 60 hours, which was using 5 executors running in parallel to test our attack strategies. And we ultimately found 9 vulnerabilities, 5 of them previously unknown in the literature. We've already looked at one of these attacks, the TCP closed-weight resource exhaustion attack. This was a new, previously unknown attack that we found using Snake. One of the other new attacks that Snake found is the DCCP request connection termination attack. This is an attack where an off-path attacker can terminate a connection if he can guess roughly when that connection will be initiated. The way the attack works is that on initiating a connection, a client sends a request packet and moves to the request state. And in this state, the only valid packets, the only valid response is a response packet. And importantly, the Linux implementation of DCCP performs this packet type check before it checks the ACK number in the received packet, and the acknowledgement number in that packet, which means that an attacker can simply send any non-response packet after the client has sent its request packet and before the server's response packet arrives, and the connection will be reset. Another of the attacks that we found is the TCP duplicate ACK spoofing attack. This is a previously known attack. It was discovered by Savage in 1999. And this attack allows clients to gain more than their fair share of bandwidth due to overly naive servers. The way this attack works is that, if you recall previously from our discussion of TCP, when either the client or a server receives data, they will need to acknowledge that data. However, if instead of just sending a single acknowledgement, the client, in this case, the client can send duplicate acknowledgements, can send multiple acknowledgements, some of which are duplicated. And then the server on its side doesn't check for these acknowledgements that have been duplicated, with the result that the server will increase its sending rate in response to these duplicate acknowledgements, allowing the client to gain much more than its fair share of bandwidth. In our tests, Snake was able to achieve throughput of a factor of 5 over the competing connection against a Windows 95 server using this attack. To your question, this is one of those attacks that was discovered in '99, so almost all of the modern implementations have fixed it. But Windows 95 being so old, this attack we can still find is still, or the Windows 95 implementation of TCP still exhibits this attack. I won't cover the rest of the attacks that we found in detail, I'll just briefly show a summary here. But I will point out that we found attacks in all of the protocols that we tested, as well as all of the implementations, and that our attacks cover a fairly wide range of impacts, from server denial of service to fairness issues to client denial of service or connection termination. So, in conclusion then, we've proposed a new efficient technique for automatic systematic testing of transport protocol implementations by leveraging the protocol system state machine. And we have implemented this technique in Snake and applied it to 5 implementations of 2 transport protocols in 4 operating systems, finding 9 attacks, 5 of which we believe to be previously unknown. And with that, that concludes my presentation, and I'd be happy to take any questions now. Thank you. Questions? Yes.
So the transport layer is pretty low level. I'm curious if you guys looked into extending this for higher level plain text protocols?
So we've considered that a little bit. Actually, this work, we've almost gone the other direction, actually. So Turret, that I mentioned in talking about other testing strategies, is actually a system developed by Christina and one of her other grad students who has graduated at this point, looking at application level distributed systems protocols. So moving to Snake then, we've actually come down a level. With that said, we are considering applying similar approaches to other protocols, like OpenFlow is one that we're looking at for SDN systems. Other questions? Yes.
I'm sorry, could you push the green button on that microphone there? That would get you. Thank you.
Sure. You had mentioned like 5,500 successful, I think it was DCCP attacks, and or 4,500.
So you're probably thinking of this number here.
Correct.
Those are the number of strategies or possible attacks that we tested. Successful attacks, we found 3 here.
Okay, thanks.
Okay, if there are no, oh, I guess we got one more question maybe.
So on the denial of service impact ones, were those
Yes.
like man in the middle or whatever your term was for the the non-proxy attacker client you had?
So off-path attacks?
Off-path,
you
sorry,
mean?
yeah.
So several of these, let me think here. The DCCP request termination attack, bottom of the slide, is an off-path attack. Both of the reset, TCP reset and SYN reset attacks, those are both off-path attacks.
Do they all require like the guessing, like the one that you showed? A little bit of chance, or
Yes,
okay.
yes. In essence, these are all, in that situation, the attacker is basically blind, so
Okay.
they have to guess. You're essentially, the attacks rely on spoofing enough packets that you are statistically right.
Okay.
Okay, if there are no further questions, then thank you very much. This concludes today's seminar.